Today we are going to discuss Huygen's principle. We'll go through the details of the Huygen's principle, and after that we'll apply Huygen's principle to verify the laws of reflection and refraction. So all these we'll discuss in today's discussion. Let's take now Huygen's principle. There are two laws given there by Huygen's, two parts are there. First one says that every point of a given wavefront becomes a new source of disturbance called secondary wavefront or wavelets. So first one is each point of a given wavefront become a new source of disturbance called secondary wavefront or wavelets. So this is the first part. Each point of a given wavefront becomes a new source of disturbance called secondary wavefront or wavelets. And second one is new position of the wavefront at a later instant is given by forward envelope of the wave at that instant. So these 2 points are there. Each point of a given wavefront becomes a new source of disturbance called secondary wavefront or wavelets. And second, the new position of the wavefront at a later instant is given by forward envelope of the wave at that instant. Now what does it mean? Suppose I take a particular wavefront. This is suppose xy representing a wavefront at any particular instant. As per the first law, every point of that is becoming a new source of disturbance. So if you take every point of this wavefront becoming the new source of the disturbance, so it is a point source here. Every point we are taking, so it is a point source. So that one will give you wave propagating in all possible directions. So we'll have the wave going out in all possible directions. And now, if you want to get a particular position of the wavefront at any later instant, that means what basically we want, suppose you want to find the position of the wavefront at an instant tau. At t equals to 0, suppose it has a position xy. And I want to know what is the new position after time tau. If I assume that c is the speed of light, so in this time duration tau, it has traveled a distance c into tau. Taking c into tau as the radius of a sphere, we'll construct spheres. And the center of that sphere will be at different points of this wavefront xy. So now you'll get a spherical wavefronts there. And here, if the wave is traveling, say from left to right with the speed c, so if I draw tangential plane, so I can get one tangential plane as x dash y dash, another is your, suppose it is your x double dash y double dash. Now x dash y dash is the forward envelope of the wave because wave is propagating from left to right, and this is your backward envelope of the wave, x double dash y double dash. So as per the second law there of Huygens, the new position is given by the forward envelope of the wave. That means the new position of the wave front after instant tau will be your x dash y dash and not x double dash y double dash. Again, you have x dash y dash as the new wave front. If you want to find wave front at another later instant, you take every point of x dash y dash as the new source of disturbance, construct the wave fronts there, and the forward envelope of the wave will give the new position of wave front at that particular instant. Now here, why not we get the wave front's position in the backward direction? Here, there is one derivation, and the result of that you will get that the contribution of a wave in a direction at angle theta. Okay, like suppose if the wave is propagating in this direction and I want to know what is its contribution at an angle theta there at the point P. So in that case, this is proportional to 1 plus cos theta by 2. So if you consider that the wave is propagating in a particular direction and theta is 0. So in that case, the contribution of the wave there will be proportional to 1 plus cos 0 by 2. So this is your 1 plus 1 by 2, or that is proportional to 1, and that is your maximum. So there is a maximum contribution of the wave in forward direction. Whereas if you consider if theta is pi, that means it is the backward direction. Like if you have the wave propagating in this direction and you want to find its position there where the angle is pi. So in that case, contribution will be proportional to 1 plus cos pi by 2, which is 1 minus 1 by 2, or it is 0. So that means it is your minimum. That is why we never get the propagation of the wave there in backward direction, or the new position is always given by the forward envelope of the wave there. Let's see how we can verify the laws of reflection from Huygens principle. So for that, suppose we take xy as a plane reflecting surface on which we have parallel beam of rays ABC incident at an angle of incidence, suppose I. They are incident at an angle of incidence I, and they get reflected as A dash, B dash, C dash at an angle R. So this R is representing angle of reflection. So what we do, suppose this is the point A and this is your B. From point A, we draw a plane which is perpendicular to these incident rays or incident waves there. Now, as you are drawing a plane which is perpendicular to these incident rays there, this is the plane which we have drawn perpendicular from point A on these incident waves there or incident rays there. So here, this is your incident wave front because it is perpendicular to the rays which is falling there, and this is the perpendicular plane which we have taken. So this one will represent your incident wave front. Similarly, from point B, if I draw a perpendicular plane, suppose this is your BN, in that case, this one will represent reflected wave front. So AM is incident wave front and BN is your reflected wave front. Let's now take a point P here on this particular incident wave front, and basically this point P is there, the wave which is coming from B. And similarly, here we take the point Q, which is there on the reflected wave front. and this is the point O, where it is meeting and is getting reflected. What we'll do, we'll try to find out what is the time taken by the wave to move from point P to O and O to Q. Basically, our aim is to find the time taken by the wave to move from incident wavefront to reflected wavefront. Remember, these waves which are there on the incident wavefronts, all points of that, they will be in same phase. Similarly, all which are there on the reflected wavefront, they are also in the same phase. So obviously, if they have moved through certain distance with a particular speed, say speed of light is c, if I'm using there, so in that particular case, the time taken by the wave will be same there for all waves which are moving from incident wavefront to reflected wavefront. We have taken a particular wave which is moving from P to O and O to Q. So the time taken by the wave to move from P to O and O to Q. This time taken, if you consider, it is your OP by C. OP is the distance traveled, C is the speed of light, and by OQ by C. This is the time taken, where C is speed of light. So now OP, now here you see, this is the angle of incidence I. This is the normal. So here, this particular angle will be 90 minus I. Obviously, this particular angle PAO, this will be I. Similarly, this angle NBO you can take, or you can take QBO, this will be also R, because this one will be your 90 minus R and this is R. So this OP can be written, if you take this particular triangle, it is your OA sin I, OP will be OA sin I by C plus OB sin R by C. For OQ, it will be OB into sin R. And this is OA sin I by C. OB can be written as your AB minus OA sin R by C. So this is your OA sin I minus sin R by C plus AB sin R by C. Remember, for all waves which are moving from incident wavefront to reflected wavefront, the time taken will be same. And if it is same for all waves, whether it is moving from point P to O, or suppose there is another one which is moving like this to this point, or someone going like this to this, for all waves the time taken will be same. And if it is same, that means this is a constant quantity. And this will be constant only if the variable term, which is the variable term here? OA. Because it is this particular is OA, for some other one it will be this particular distance, for other it will be like this. So this must be independent of OA. Then only it will be constant there. And for that particular term to be constant, for this time taken to be constant, why it is to be constant? Because for all waves which is moving from incident wavefront to reflected wavefront, time taken is same. So for this time to be constant, it must be independent of OA. And how it can be independent? it will be independent if its coefficient is 0. So for that, therefore, its coefficient sin I minus sin R should be 0, or sin I is equals to sin R, or I equals to R. So angle of incidence is equals to angle of reflection. This is the first part of laws of reflection. Second thing, as the incident ray, reflected ray and the normal, they all are lying in the same plane. So obviously the second law is also verified. Incident ray, reflected ray and the normal at the point of incidence, they are lying in the same plane. So second law of reflection is also verified. You can just take it in this way also. If these are the incident rays, then the incident wavefront will be a plane perpendicular to this. It will be perpendicular to this. So this is your incident wavefront. Similarly, this is your reflected wavefront. So this is reflected rays. So this is your reflected wavefront, and this is the normal. So incident ray will be perpendicular to the incident wavefront. So if this is the plane, in that case perpendicular to that will be in this particular plane of the board. If it is the reflected wavefront, in that case reflected rays will be perpendicular to that. That means it will be perpendicular to the plane of the board. Obviously, incident wavefront, reflected wavefront and the normal there, if you consider, and accordingly you find the direction of the incident ray, reflected ray and the normal at the point of incidence. They all will be lying in the same plane. So second law is also verified. That way also you can explain. This is the proof of laws of reflection by Huygen's principle. Now see the proof of laws of refraction by Huygen's principle. So what we are doing, we are assuming that this xy is a plane surface which is separating two media of refractive index, say mu1 and mu2. And say the speed of light in the first medium is c1 and in the second medium it is c2. We have A, B, C as the incident rays which are striking at an angle of incidence I, and they get refracted at an angle R here. So this is R. So again what we do, we draw a plane which is perpendicular to these incident rays. That means this AM, this one will represent incident wavefront. Similarly from B, if I draw a perpendicular plane, this is suppose your BN, this will represent refracted wavefront. And now we have the point P here, this is Q and this is your O. So again we'll take what is the time taken by the wave to move from incident wavefront to refracted wavefront. And for that we'll take a typical ray, say P to O and O to Q distance, how much time it has taken to pass through this particular distance. And this is P is a point on the incident wavefront, Q is a point on the refracted wavefront. So the time taken by the wave, to move from P to O and O to Q. So this will be equals to OP by C1, because now we have assumed C1 as the speed of light in the first medium, and OQ divided by C2, because C2 was the speed of light in the second medium. Again, this OP, if we have to take, if this angle is I, this is the normal. Okay. So in that case, this particular one will be 90 minus I, because this AM is normal to these rays there. So obviously this particular angle will be I. In the same way, this particular angle will be R, because this will be 90 minus R, this particular angle, and here this particular angle is R. So OP can be written as your OA sin R, because this is perpendicular. For this angle I, this is your perpendicular, this is the hypotenuse here. So in that case, it is OP by OA is sine I, or OP equals to OA sine I by C1, and OQ can be written as your OB sine R by C2. This is again OA sine I by C1. OB can be written as your AB minus OA sine R by C2. OA sine I by C1 sine R by C2 plus AB sine R by C2. Now again, this is the time taken by the wave to move from O to P and O to Q. That means this is the time taken by the wave to move from incident wavefront to refracted wavefront. Time taken by all waves to move from any point on incident wavefront to the refracted wavefront will be same there. So if it is same for all waves, that means this time has to be constant. And for this time to be constant, how it will be constant? If it is independent of OA. So as the time taken is same for all waves from incident to refracted wavefront. Hence, it must be independent of OA, because this is the particular term which is different for one wave to other. And for that, therefore, its coefficient should be 0. That means sine I by C1 minus sine R by C2. This is 0. And that is your sine I by C1 equals to sine R by C2. And that gives you sine I by sine R equals to C1 by C2, which is constant, which is your mu2 by mu1. And this is your Snell's law. So we have proved that sine I by sine R is equals to a constant for a given pair of media. That is your Snell's law. So first part we have proved. Again you see that incident rays, refracted rays and the normal at the point of incidence, they are lying on the same plane. So the second law is also verified. Or alternatively, you can say as this AM, which is a incident wavefront which is perpendicular to the plane of the board. This BN, which is the refracted wavefront, again it is perpendicular to this board. So in that case, rays will be perpendicular to these wavefronts, because wavefront is always perpendicular to the direction of propagation of the waves there. So if the incident wavefront is perpendicular to the plane of the board, the incident rays will be lying on the plane of the board. If this is your refracted wavefront, obviously refracted ray will be also lying in the same plane of the board. So the second law is also verified here. So that way also you can say that the second law is verified. So this is how you can prove laws of refraction by Huygen's principle.